All right, today we're going to tackle two concepts that are, seriously, everywhere in data science, from A/B testing all the way to predicting election outcomes. I'm talking about the Bernoulli and binomial distributions. Now, they might sound a bit complex, but trust me, they start with a single super simple idea. So let's break it down.
Just think about the last time you were scrolling online. Did you click buy or did you move on? Did you like that post or did you just keep on scrolling? Every single one of those moments is a simple yes or no decision. And that binary choice, that's the foundation for literally everything we're about to explore.
And that right there is the key idea we're going to run with. We're starting with just one single yes or no, our one little building block, and then we're going to see what happens when we start stacking those blocks together to predict much bigger, much more complex results.
So here's our game plan. We'll start with that single choice and define the Bernoulli trial. Then we'll see what happens when we scale it up with the binomial distribution. After that, we'll put it to the test with a real-world shopping cart example before we wrap up with the final tally. Okay, let's kick things off with that single choice. All right, let's really zoom in on this, that one fundamental moment of decision where you have a single event with only two possible ways it can go. So, in the world of statistics, this has a name. It's called a Bernoulli trial. It's basically any single experiment where the result is one of two things. A coin flip, that's heads or tails. A quality check on a factory line, it's pass or fail. A customer visits your website, they either make a purchase or they don't. That's the whole deal. One event, two possible outcomes. Simple as that.
And the tool we use to describe this single trial is, you probably guessed it, the Bernoulli distribution. It's honestly the simplest probability distribution there is, and it's our starting point.
Okay, so what we're looking at here is how we actually label these things in math speak. We just call one outcome success and give it the number 1. The other we call failure, and it gets a 0. The probability of success we just call p. And since there are only two options, well, the only other option is failure, so its probability has to be whatever's left over, which is just 1 minus p. And this chart, it shows it all perfectly. Now, it's got a fancy name, probability mass function, but don't let that throw you. All it's doing is showing us the chances of our two outcomes. You can see there are only two bars. The chance of failure, at 0, is 1 minus p, and the chance of success, at 1, is p. That is the entire distribution. And the best part? The math here is super straightforward. The mean, which is kind of like the average result you'd expect over time, is simply p. And the variance, which tells us how spread out the results are, is just p times 1 minus p. It's really elegant in its simplicity. Okay, so we've got our single building block down, right? The Bernoulli trial. So what happens if we do it more than once? Like a lot more. This is where it gets really interesting and honestly, super powerful. So this is how we scale up. It's a simple 3-step process. First, you start with your single Bernoulli trial. One customer, one choice. Second, you repeat that same trial a fixed number of times. Let's call that n. And third, you just count them up. We're not looking at one person anymore. We want to know about the total number of successes out of all those trials. And this quote right here just nails it. A binomial distribution is simply what you get when you run a bunch of independent Bernoulli trials. So if you only run one trial, if your n is just 1, then you've just got a plain old Bernoulli distribution. It's like the Bernoulli is the single Lego brick, and the binomial is what you build with the whole box of them. This table puts it all side by side, super clearly. Bernoulli is just one trial. Binomial is n trials. And check out the mean and variance. See that? It's the exact same formula as Bernoulli, but we just multiply it by n, the number of trials we're running. It just makes sense, right? The more trials you have, the higher your expected number of successes will be. Okay, that's enough theory for now. Let's get our hands dirty and see how this actually works in the real world. This is exactly the kind of problem you'd see in a data science interview or a real business meeting. So, picture this. You're running an e-commerce site. You're getting a ton of visitors, and you want to figure out the chances of getting a very specific number of sales. This is a textbook binomial problem. Okay, so let's plug in some numbers. First, n, the number of trials. That's our total number of website visits, so let's say 100. And you got to remember, each one of those visits is its own little independent Bernoulli trial. Next up, we need p, the probability of success for any single visit. Let's say your site is doing great, and you have a historical conversion rate of 75%. So our p is 0.75. This means for any person that lands on your site, there's a 75% chance they're going to buy something. And last, the big question, what are we actually trying to find out? Well, let's say we want to know the odds of getting exactly 75 purchases. This is the specific outcome we're interested in, Rx.
So that all leads us to this one big question. If your average conversion rate is 75%, what are the actual odds that you get precisely 75 sales from your next 100 visitors? Now, your gut might tell you, hey, the average is 75, so the chance of getting exactly 75 must be pretty high. But is it?
And boom! The answer is just 9.17%. Let that sink in for a second. Even though 75 is the single most likely outcome, the probability of hitting that exact number is actually pretty low. Why? Because it's way more likely you'll get a number close to 75, like 74 or 76. And that right there is a huge insight when it comes to forecasting.
This chart really paints the whole picture for us. See that tallest bar right in the middle? That's our 9.17%. But the beauty of the binomial distribution is that it lets us calculate the probability for every possible outcome. This gives us a full-on probability map of everything. It tells us what's likely, what's a long shot, and everything in between.
All right, let's wrap this up and really lock in the big ideas from today.
Okay, so if you walk away with just one thing, let it be this. Bernoulli is the atom. It's that one single trial with two outcomes, success or failure. Binomial is the molecule. It's what you get when you run a bunch of those Bernoulli trials and just count up the successes. And since we're counting whole things like sales, we call these discrete distributions.
And that kind of leaves us with one last question to chew on. We've totally nailed how to handle things you can count, right? Sales, coin flips, you name it. But what about stuff you have to measure? You know, things like height, weight, or time, things that can take on any value in a range. Well, that, my friends, takes us out of this world of discrete probability and into the amazing realm of continuous distributions. And that's a story for another day.